The test is from 4.1 through 4.4. You can expect between 7 and 10 or 7 and 9, I forget what the actual number is, multiple choice problems. You can expect between like 6 and 8 short answer problems. And then the free response, you're going to have 4. The free response, you're going to have to do the first 2. Then you're going to have to choose one of the next 2 as the third problem. And then choose one of the next 2 as the fourth problem. Okay? So same setup as the last test. You did 2, and then you chose 2 out of 4, really. But I'll give you 2 problems, you choose one of them. I'll give you another 2 problems, you choose one of them. So that's the general setup for the free response. For the free response, here's what you can expect for problems. You can expect a problem having to do with weight on different planet. We did a few of those. We did those in the notes too. So weight based on a planet. Okay? You can expect a problem with a force at an angle.
You couldn't give us the coefficient of the planet, right?
The coefficient?
Like, I mean, the gravitational force.
You might have to determine that value. That might be what I'm asking you for. But you have something to do with gravitation on a planet. Or maybe I'll give it to you and tell you to find the mass, depending on what it is. So force applied at an angle is the second type of problem. The third type of problem you can expect has to do with friction. So I'll introduce friction. Okay. And the fourth type of problem you could expect will be an inclined plane. And the inclined plane, you'll choose one of 2. There'll be 2 inclined plane problems at the end. You choose one of them. There'll be 2 problems that are difficult with friction or more elaborate. You'll choose one of them. There'll be a pretty basic problem with forces applied at an angle. And then there'll be a problem with weight on the planet. Okay?
When weight on the planet, is it, when it says like it is 1 point, like from the problem set, when it's like 1.4 times that on Earth, you do not multiply 1.4 times the gravitational pull on Earth, no, right?
You could do that and then multiply by mass, and you'll get the weight on the planet. Or you could just take the weight on the planet you get and multiply that by 1.4. Either way.
Okay.
If you're given a mass of an object and you want to find its weight on another planet, you could do mg on Earth times whatever the multiplier is, 1.4, and get the weight. Or you can take m and then multiply Earth's g value by 1.4. In the end, you get the same answer, because you're still just doing m times g times 1.4, because it's 1.4 times more than Earth. Okay? Okay, that's the general ideas. For multiple choice, the type of questions you'll expect would be questions from mainly sections 4.1 and 4.2. You could also expect questions on mu values. So if I told you, here we go, hypothetical. If I told you that the mu s value between 2 surfaces is 0.85, and I gave you 4 multiple choice, and I said, which of the following could be the kinetic coefficient of friction? Here's your 4 choices. Negative 0.2, 0.2, 0.85, or 0.9. Which could be the coefficient of kinetic friction for a problem like this? B. Why not A? Well, A is less. You said it's less.
Well, you can't have a negative.
Okay, so be careful with your statement. It is less, but it's got to be positive. So the answer would be B here. 0.85 would be the same, so obviously it doesn't make sense. And 0.9 would be the other way around. Okay? The other way around.
The static friction is greater than the kinetic friction?
Yeah, so the question is, if static friction is 0.85, find kinetic friction. Which could it be out of the possible ones? Okay? And remember that kinetic friction has got to be less than static, so the only one that makes sense is choice B. A doesn't make sense because it's negative. The others don't make sense because it's the same, and one is greater than. Those are the kinds of questions. What else? What are the kinds of questions? I might ask you things like, as the normal force goes up on an object, what happens to the friction force? Well, that also goes up because they're directly related. I don't know. Let's go to an inclined plane problem. Okay? Because those are the ones that people have been. So forces at an angle as opposed to inclined planes. Forces at an angle are when you're on a horizontal surface and you're applying a force to an object, but it's at like an angle of 60 degrees. For x component of the pole, you use FP cosine theta. For the y component, you use FP sine theta. Normal, just like we did with projectile motion. Inclined planes is where you break up your Fg, the gravitational force, into its x and y component using not cosine of theta for x, but cosine of 90 minus theta. And instead of cosine or sine of theta for the y, you use sine of 90 minus theta. And I went over where that comes from in the video. That's that part. But just to remember it for now. So let's look at an inclined plane example.
Mr. Hunt,
Yeah.
what did you say about as the normal force increases?
If you had a problem that said, as the normal force increases, what happens to the friction force? But if you remember, friction force equals mu Fn. So as Fn goes up, the friction force will also go up. Okay? As the normal force goes up, the friction force also goes up. They're directly related. So let's say we have an inclined plane, and we are trying to find the acceleration of the object down the ramp. We're not given the mass of the object. We're told that the angle of the inclined plane is 30 degrees. We are told that the kinetic coefficient of friction is 0.8. And we're looking for the acceleration. Let's just go with that. I feel like there's one piece of information I'm missing. You don't need the mass, and you saw that in the video. The mass actually drops off.
I don't get how the mass. I mean, I
So we'll do this, and we'll show it.
I get how it drops off, but it's just.
It's mind-boggling to you?
If you were to be given mass and use mass in the
Think-
final equation, you would get the same answer.
Think about it for a second. If you had... Unlock that, please. Unlock that before you open it. Turn the thing. If you had to find the coefficient of friction between two surfaces, right? It's a property based on the surfaces themselves, not the mass.
Yeah.
So if you solve for mu k in these problems, mass shouldn't matter.
Okay.
It's not dependent on the mass, ever. This surface interaction between my hand and this table, the mu value, is a constant. If I push harder, mu is still the same. The force of friction changes if I push harder. Right? If I push lightly, my hand can move smoothly. But if I push hard, it's tough to move, isn't it? Because Fn went up. But the mu value hasn't changed. Ff is what's changing when I apply more force. Mu is constant based on the surface interactions. That's why the value of m is dropping off in these problems, okay? Because we're determining the mu value. On the right-hand side, those are all values we're given in this problem, yeah.
So like on all problems, in the problem sets, like I would always use the equation to find a, F equals ma.
Mm-hmm.
So like without the mass, how would you
Let's find out and take a look. I already went over it in the video. If you guys watched it, I went over 2 examples of this. So it should be obvious for that part, but let's go through it. We have an object here. Let's say that it's got, again, the friction holding it up the ramp like this. We've got the normal force acting out of the ramp perpendicularly at a 90-degree angle. Now, here's the part that you learned in the video with the weight. The weight is the interesting component. The weight of this object clearly acts straight down. The weight of every object acts straight down. So I could start by drawing it straight down, and I'll draw it in blue, because we're not going to use it. We're going to erase this eventually. This is the weight of the object pulling straight down. But it really pulls at angles. So part of it is pulling it down the ramp like this. That's what's causing the object to actually move down the ramp. The x component of the actual weight. And part of it is actually pushing it back into the ramp here. So really, what we're doing for this problem is we're ignoring Fg. We're looking at its components to help us for this problem. Okay? Now, the idea that we use cosine and sine of theta still applies. But remember, for an inclined plane, that we're going to use 90 minus theta for each of these. So for Fgx, we're going to use Fg times the cosine, because it's in the x, of 90 minus theta.
FG or MG?
Fg, which is indeed mg. So either one is fine, yes. We're going to replace Fg with mg eventually. Okay?
For all the problems where like it's on a
Inclined plane.
Do we just, instead of just FG, FGY and
Mhm.
FGX?
Always. Okay? Now, in the x direction, this is where it gets tricky. And I'm going to draw this in another color. Let's try green. Draw your axes on yours right now. Tell me where your x and y axis would be. And this is what's confusing. This is why I talk about tilting your axes. How would you draw your x and y axis? Go ahead and draw it on yours. And then you could correct it if you're incorrect. I'll draw it up on the board in a moment. I want you to see if you know what you're doing. If you can't do this right now, what I'm saying, then you really need to watch that video. Because I went over this a few times, and it's obvious that people haven't done it. Okay, I can tell by the amount of views. Yeah. Not as many as the people that should have. Look in the y direction. This is what your y-axis should look like. That's the y-axis in this problem. Here's the x-axis. Okay, that's the x-axis. So when you do these problems, you need to tilt your head so that your head is looking along the normal force vertically. You see what I'm saying? I'm tilting my head so that it's oriented with the normal force. Then draw your axes from there. Is that clear? So down the ramp is in the positive x direction in this problem. In the notes, I think the inclined plane was drawn the other way. So in that example, down the ramp was in the negative x direction. So it's going to change based on the problem. Again, if I had a ramp like this, then this is the x direction, and that's up the x-axis here. So down the ramp would be considered a negative in the x for this kind of a plane. But for the plane that we're looking at, this is down the ramp, that's the x-axis, that's the positive.
Oh wait, is it like a line?
Well, how do you know how?
One at a time. Is it a line?
Can you ignore that, to figure out which one's positive and negative? That didn't really.
Oh, here's how you figure it out. Look at the normal force. That's positive y. And then draw your axis normally after that. If this is your y-axis, and y is up positive here, x has got to be positive this way. Okay? Tilt your head and do it.
Oh, so kind of see like a graph?
Yeah, guys, that's what you're overlaying a Cartesian coordinate, a graph on top of here. It's exactly what you're doing. You're overlaying your xy axis for math on top of this. Okay?
How do you know which way to draw the incline on a problem? How do you know which way to draw the incline?
It doesn't matter. Either way is fine. And what you'll notice is that all your forces will be negatives, but your acceleration will be the opposite. But that's fine, because it should be negative then.
As long as you're consistent.
Absolutely. As long as you're consistent in the problem. If you draw your diagram like this, you need to do your math correctly like this. So FGX would be positive. FFK would be negative in this example. But if you drew the ramp the other way, they would switch signs. Okay? Nick?
FFK, is that dynamic friction?
Yes, kinetic or dynamic. Yep. Same thing. Okay? And it's acting that way because we're saying this object is moving. We're looking for the acceleration, so it's got to be dynamic or kinetic. Okay? All right. So in the x direction, let's write what we've got. 10? Thank you. Remind me at 5. Stop me at 5. In the x direction, what's acting in the negative x direction or up the ramp? Remember, up the ramp is negative x. What's acting up the ramp, everybody? Yeah, friction. So we put negative FFK for friction. Negative FFK for friction. What's acting down the ramp or in the positive x direction, everybody? FGX. That's acting down the ramp, FGX. We have acceleration in this problem, so we can't just put 0 at the end. We have to put equals MAX. We have acceleration, the object is sliding down the ramp. Some of the forces, this is James's question, F equals MA. Some of the forces, this is F right here, equals MA. Okay? So we got two forces acting on this body. So instead of F equals MA, we have negative FFK plus FGX equals MA. Now, what else do we know about the x direction? What can I replace those with? In the x direction still. Still in the x direction.
You can replace FFK with FN. Is UFN?
Yeah, mu Fn. So we replace the negative FFK with mu KFN. Carry down the negative, please. Because it's a formula. It means you need to look at your formula sheet and you need to study a little more if you're asking that question right now.
You can also replace FGX.
Yeah, what's FGX replaced with?
MC cosine minus theta.
Very good. So that's what we can replace. Remember now that the force of gravity in the x direction is really, this FGX here is really FG cos of 90 minus theta. But instead of putting FG, just put mg in its place. Because the formula for FG is mg. Mass times gravity. But remember, it's the x component, so we tack on that cosine of 90 minus theta. That's really all we can do right now, simply because we're looking for acceleration. But we don't know Fn. We know everything else. Actually, we don't know mass either. But don't worry about the mass, because we'll see the beauty behind it, and that's going to cancel out. But we don't know Fn. So what should we do at this point in time if we don't know Fn? Whenever you don't know Fn in the x direction, what should you do? Go to the y. Go to the y direction. Why should I go to the y? James.
Because whatever the FGY is, the FN will be equivalent.
Yeah, take a look at the diagram here. Fn is acting in the y, and so is FGY. Those are equal and opposite. So it turns out that they're going to be the same numbers. Let's write our equation, though, to show that. I'll show your hand. Give me a sec. So in the y direction, acting... I'm going to move this down, actually, first. Let's leave a little room. In the y direction, acting out of the ramp, in the positive y is Fn. Whoa. Acting into the ramp is FGY. So minus FGY. Now, the acceleration in this problem confuses students because they think it's both in the x and the y direction, which I understand because it's at an angle, right? But remember how we tilted our axis a moment ago? Wasn't the object moving along the x-axis only? Think about our axes. How did you draw the axis over the ramp? The surface of the ramp was the x direction. So this object is only moving along the x-axis. It's not moving up and down off the ramp at all. So this is just 0. MA is just 0 here. Okay? Now, add FGY over, giving us Fn equals FGY. But FGY is what? Geo. No. FGY. The weight in the y direction. The weight in the y direction. Geo, look up here. This was the weight in the x direction, right? So what would the weight in the y direction be? Just what's the only difference? Okay, so what would it look like? Tell me. Fn equals, you don't have to whisper in his ear, please. Fn equals? Yeah, but don't forget your mg, right? Remember, this is like your weight times the x component. So we want to do the weight again, mg, but we want the y component, which is sine. Okay, that's the Fn value for that problem.
This is back to the x. Why don't we simplify by dividing? Why wouldn't we solve it for a and divide by m?
We can. Guys. Lou? Dang, I called him Nick before again. Lou just asked the question. Nick just asked the question. I think you guys are messing with me now. I can't even tell. Nick just asked the question, why didn't we solve for AX? We could have. You could just solve for AX by dividing by M. And I'm going to do that anyway. Okay? So if you go back up here and you want to divide by M, okay, you can go ahead and do that. And we'll just have AX by itself. Okay, so divide by M. That's the solution for AX, yes. The reason I stopped, Nick, is because I noticed that Fn was unknown, and before I went further, I said, let me go take a look at Fn. Alright? So now, look at the bottom right of the screen. Okay, we're going to take that value from the bottom right down there. Whoa, I can't move this slide apparently. We're going to take this value down here, I'll circle it, and we're going to substitute it in right here for Fn. mg sine of 90 minus theta is going to go in for Fn where it's circled. So our answer becomes the following. So it's in green. Look at the green in the middle. I replaced Fn with mg sine of 90 minus theta. Now what do you notice? There are three terms, and I want to emphasize this because people are getting confused in the other class. This whole thing, take a look, I'm circling. This whole thing is the first term. Plus, this whole thing is the second term, divided by another term. Every term has mass. Every term has mass in it. So what can I do? I can cancel the masses. If it's not clear to you, here's what you can do on your own. See the m here and the m here, you can factor m out in front. And then the m cancels with the m. So I'm just going to cancel them because I see it's in every term. If mass is in all the terms, it drops off. So my final solution here So my final solution, I'll put in pink at the bottom for acceleration, is going to be negative mu k g sine of 90 minus theta. Oops. Guys, stop. Plus g cosine 90 minus theta equals ax. If you would like to, and I did this in the other class, you can factor out a g because it's in both terms. You can put g out in front, and you have the same answer still. Why did I get rid of the m's? Because they're in all terms. M, M, M. It's in every term. So it's like having an m in the numerator and an m in the denominator. It would cancel. It's in terms though. Dylan, look up top. If you were to factor out an m out in front, the top would become this. I'm going to write it out. If I factor it out an m, here's what we would get. That's what you would get up top, Dylan, if you factor out an m. So you'd be left with all this up top with an m out in front. The m out in front cancels with this m right here. You see that? And what are you left with? You're left with all this, which is exactly what we have if you just drop off the m's, which is exactly what we have right here. This right here is this term. So if you need to factor out an m out of both terms, that's what I was saying before, to show that these m's cancel, to make yourself see that, that's fine. But if you have an m in all three terms, you can drop it off. Okay? So the result is this. The acceleration in this problem has nothing to do with mass. That's why you weren't given the mass in the problem. Okay? I might ask you on the test to solve for mu k and not the acceleration. It's the same exact problem, but you need to rearrange this and solve for mu k. Alright? You can factor out a g out of both of these. It's fine. It doesn't matter. But the clear point is this. The answer for acceleration is a function of the coefficient of kinetic friction and the angle only. G is the same because we're on Earth.
No, I see why it didn't make sense to me originally, because when I was doing these problems, I would convert like the sine of 90 minus theta into a number immediately. I wouldn't leave it as that.
I would leave it generic for these problems, and then you'll see the masses cancel. Because if you don't, the masses don't drop off and you don't notice it.
That was the first thing I was doing, was making everything a number.
Now, you would need the mass if I gave you a problem and you needed like the friction force. Because remember, the more mass, the more friction. Guys, last thing.